Part 2 of the Chapter 3 practice quiz. Here we have a 12 kilogram truck tire. Y is tied on horizontal rough surface. The tire is attached to two light ropes that pass over a light frictionless pulley hanging on the tails X and Y. X is 5 kilograms, X and Z, and Z is 3. What is the magnitude of deceleration in meters per second squared of the frictional resistance is 9.6 newtons. This is a Fletcher's trolley type problem. It's obviously a little different because this time you have tails on both ends, but it's no more difficult. So we're just going to start off with a free body diagram. Here. So once again, with the Fletcher's trolley problem and the outwards pulley problems, when we're doing the free body diagram, we do the free body diagram for the entire system. So if tail X is 5 kilograms, tail Z is 3 kilograms, then obviously 3 kilograms, obviously X is going to go down, Z is going to go up, and the tire is going to move in this direction. So our free body diagram for this, well, this mass here will actually be 5, 12, and 3. So that's actually going to be 20 kilograms that we're dealing with because that's the mass of the entire system. And we have two forces. So gravity is making the tire go, is pulling this one down and making the tire go in this direction. So we're going to call that FGX. And the gravity acting on tail Z is going to make it go in this direction. So we're going to call that FGZ. And then we just have to decide about the frictional force. And this is pretty important that you decide which direction is the frictional force. It's not difficult, because obviously if this pail is going down and the entire tire is going to the left, then the frictional force must be to the right. So FF is to the right. So we're just going to do right there. Your frictional force is to the right. That's very important because you have to make sure you get the signs correct. And from there, it's actually quite straightforward. We want to find the acceleration, therefore we need to find the net force. What is the net force? It is the force of gravity of X, which we're going to call negative because it's going down, is plus the force of gravity of Z, which we're going to have to call positive because Z is going up, plus the force of friction, and the force of friction is also going to be designated as positive. It's very important that we get the signs correct in this problem because the force of friction is also going to the right. And once you've got that and you've got the sign straight, it's pretty straightforward. It's just mg plus ff. This is going to be 5 times negative 9.81 plus 3 times positive 9.81. Yes, you must make that positive because if we designated the first one as being negative, the other force is going in the opposite direction, so therefore it must be positive, which is a little counterintuitive having a positive 9.81, but that's the way we must do it, plus a positive 9.6, because once again, we designated those two directions, the blue one here and the purple one here, as being positive, and the red one over here is negative. Therefore, we must have positive signs for both of those two. So you stick that into your calculator, and it's going to turn out to be negative 10.02 newtons. That's the net force of the acting on the tire, or acting on the whole system. And then we want to find the acceleration. Acceleration always equals the net force divided by the mass. Negative 10.02 newtons divided by the mass. And what mass do we use? We always, for these type of problems, use the mass of the entire system because the entire system is accelerating at the same rate. Yes, in different directions, but at the same rate. So it's 20, and you end up getting negative 0.5 meters per second squared. Okay, and it would just ask for the magnitude of the acceleration. And the reason it only asks for the magnitude is because they're all accelerating in different directions. It's accelerating down, down, and this one's accelerating to the left, and this one's accelerating up. So they just want the magnitude, otherwise we have to express the answer in 3 different directions. Number 5, cement block of mass 30 kilograms is accelerating down an inclined plane that makes an angle of 30 degrees with horizontal. The coefficient of friction is 2.1. What is the block's acceleration? Okay, so what do we got here? Let's draw a free body diagram. Let's just add it to the one that's already there. So what have we got? It's accelerating down. It's accelerating down, and therefore what force is pulling it down? You should know from the examples that we've done. Is the force of gravity parallel to the surface that is pulling down the slope? What is pushing it up the slope? Obviously the frictional force, because we're dealing with kinetic friction here. And then of course we've got the normal, or the gravity is going down, which is already designated for you, already shown. We've got the normal force, which is always perpendicular to the surface, that's going in that direction. And remember, for these problems with inclined planes, we're always going to separate the gravity into its components. So it has this component here, which we call Fg perpendicular. And Fg perpendicular is always equal and opposite to Fg, the normal force. So it's the normal force. This one here is Fg perpendicular. And then, of course, we have this one right here, Fg parallel, which is essentially the force that's making it, it's the component of gravity that's making it go down the ramp. Right? In terms of finding the acceleration, we need the net force, and then we're just going to use F equals F net over M. The net force horizontally, or not horizontally, but in the direction that's moving, so in this direction here, is going to be Fg parallel plus Ff. Okay, and we can find Fg parallel quite easily by just taking the triangle. This triangle right here, Fg perpendicular, Fg parallel. We know that this is 30 degrees because that's 30 degrees, so this one is automatically 30 degrees. We know that the mass is 30 kilograms, and so 30 times 9.81 equals 294. So this is 294.3 newtons. And we can use sine and cosine to find out the force of gravity perpendicular and the force of gravity parallel. So the sine of 30 degrees equals the force of gravity parallel divided by the hypotenuse, 294. And therefore we get the force of gravity parallel to be, so sine 30 times the answer, and we get 147.15. Okay, let's just go over here and do the cosine of 30 equals Fg perpendicular divided by 294.3, and we get the force of gravity perpendicular, which we will need. Cosine 30 times 254.87. Okay, so at this point, we can put in this one, the force of gravity parallel, and I'm going to make it a negative because it's accelerating down the slope. So we'll just make that one a negative, and we'll make the force of friction positive. Okay, we don't know the force of friction, we're given the kinetic coefficient of friction. And of course, we have our formula, and our formula is that the force of friction equals mu times Fn. Mu, 0.12 is given to us in the question. Fn, so back to our original diagram, Fn, as you can see, is equal and opposite to Fg perpendicular. And that's why we have to solve for Fg perpendicular. The box is not accelerating in this direction, up or down in this direction. So it has a net force of 0, therefore Fn and Fg perpendicular must be equal and opposite. So we can use right here the Fn that we calculated previously. In this part of the question, that will give us a frictional force, 1 times 254. That gives us 53.52. That's my frictional force. Once I've calculated my frictional force, I can go back up to here. 53.52 to get the net force. That gives me a net force of negative 93.63. And then back up to here to get my acceleration. 93.63. The negative is, it's relevant, but it just tells you that it's going down the slope, divided by mass. When you get an answer of 3.1. 3.1 meters per second squared. Okie dokie. On to number 6. The last one is an Atwood's pulley problem. It's kind of similar, it's very similar to the first one we did, question number 5. We have a 2 and a 1 kilogram mass. Obviously, the 2 kilogram mass is going to accelerate down, the 1 kilogram mass is going to accelerate up. Neither will accelerate at the force of gravity, well, with the acceleration due to gravity, because they're kind of offsetting each other. And our free body diagram is always going to, for Atwood's pulley problems, is going to be one of them going this way, the 2 kilogram one, and it's going to be the force of gravity because gravity is pulling this one down. And we'll go 2 kilograms, and gravity's pulling the other one down, but it's accelerating up. It's going in the in terms of the whole system, it's going in the opposite direction. So this is going to be Fg1, and the mass of this whole thing is both of them, 3 kilograms. All right, and the F net therefore is going to be Fg1 plus Fg2. Force of gravity acting on 1 is going to be 1 times gravity. Now in this problem it says that gravity is 10, so that'll be nice and easy. But since this one's accelerating up, and since these two forces here, this force in here are going in opposite directions, then one of these has to be positive and the other has to be negative. So we're going to say that this is positive 10. And for this one, mg, we're going to say that this one's negative 10. Positive 10 plus negative 20 is negative 10 is the net force. Once you've got the net force, the acceleration is going to be the net force divided by the mass. Negative 10, again, the negative is not necessary as long as you can identify which way each mass is accelerating. And again, in the question it says what is the magnitude of the acceleration, so therefore the negative is relevant for this specific question. Divided by the mass of the whole thing, and you get 3.3 meters per second squared, which means that the 1 kilogram mass is accelerating up at 3.3 meters per second squared, and the 2 kilogram mass is accelerating down at 3.3 meters per second squared. That's it. Here's the quiz on chapter 3. Is going to look similar to that one. you can do those questions, you should be good to go. Take care.